So guys, I want to start today with you looking at something on the front side of our equation sheet. There is a section right on the front that says, it's got a heading, equilibrium. And I just want you to look at the first two lines there, okay? And this is good that I'm pointing this out because this will be good for us to review a little bit of what we did last class. All right? The first line says KC. Do you remember what C stands for? Concentration, okay? What's right there, that's your equilibrium expression. It's the way to set up the equilibrium expression for some reaction. Products divided by reactants, your coefficients become exponents. What state or states of matter are you permitted to include in a KC expression? Gases and aqueous. Not liquids, gases and aqueous. All right, just one line below it, it says KP. What does P stand for? Pressure, okay. Same deal, products over reactants, your coefficients still become your exponents, but notice there are no brackets, so concentrations, molarities, that's gone. What state or states of matter can you include in a KP expression? Gases only. Okay, good. Now, you'll notice, guys, in this equilibrium section, there is a whole bunch of other stuff. All right, Ka, Kb, Kw, some stuff about pH. That is material that we're going to cover probably about third quarter. It's on acid base. Okay, so for the moment, you can ignore it, but there is some good stuff here. Okay. So we have talked about the equilibrium constant K. There is something else, different variable, called the reaction quotient. Its variable is a capital Q. A lowercase q means something else in chemistry, so make sure you get that right. And here's the deal with Q. It is calculated exactly the same as K. Now, what do I mean by that? I mean products divided by reactants. The only difference is those molarities or partial pressures, it doesn't matter which K you're talking about, they are molarities or partial pressures not at equilibrium. And typically, it doesn't have to be this way, but typically it's going to be initial conditions right when the reaction begins. Okay? And if I know what you're probably thinking, you know, the title of this chapter is equilibrium. You know, why would we ever care about a situation that isn't at equilibrium? Well, here's the thing. You know, all reactions at all times are not at equilibrium. Sometimes they haven't yet reached equilibrium, or maybe they've gone too far. We're going to calculate Q at times not at equilibrium. We're going to compare it to K, and that's going to tell us, where is this reaction? Do we need to go a little bit further to get to equilibrium? Have we gone too far? Do we need to come back a little bit? Q tells us where we are in this reaction. All right? Now, here's the thing. I'm going to put some information up here that I do not want you to memorize. I want you to understand it. All right? And we're going to use the simplest possible reaction you could think of. A goes to B, right? And both Q and K, if you'll remember, are calculated products over reactants. Okay. Well, let's say that we are not at equilibrium, and I'm going to give you some numbers to work with. Let's say that my product B has a molarity of 1 molar, and my reactant A has a molarity of 4 molar. Okay. Remember, Q is calculated the same as K, so I'm going to plug these numbers right in here. 1 divided by 4. Okay, so that's my reaction quotient. I need to give you a K value, don't I? I'm just making these numbers up. Let's say the equilibrium constant is equal to the number 2. Right? Let's compare Q to K. Do we all agree that 2.5 is less than 2? Nod your head. Yes, very good. All right. This says shift to the right. Please don't memorize that. I want you to understand this. Q is less than K. Here's how I want you to think of it. Q being less than K means it's not big enough. Okay? Focus on just the numerator if you like. We need this number to be larger. I need my numerator to be larger. Well, what's in the numerator? Products. That means in this reaction, A to B, I have not made enough products. I need to make more. Well, how do you make more products? By moving in this direction, using up some of my reactants to create more product. Okay, so if Q is less than K, we shift to the right. You could also say shift in the forward direction in order to get to equilibrium. But again, please don't memorize it. Think of it as, do we have enough product, too much, not enough? That's what I want you to think about. In this particular circumstance, we haven't made enough product yet. So we need to make more. Let me change some of these numbers. All right, this time I'm going to say that my product B is at 10 molar, and my reactant A is at 2 molar. Plug in the numbers. Okay. We all agree that 5 is greater than 2. Very good. Okay. Again, let's think about what that means. Q is greater than K. Q is too large. Think about just the numerator again. If this number is too large, that means my numerator is too large. You could also say your denominator is too small. It doesn't really matter how you think of it, but just focus on the numerator if that's easier. This number is too big. I have too much product. I need to get rid of some of it. How do you do that? By shifting this way. Use up some of this product to create more reactant. So in that situation, you would shift to the left. You could also say shift in the reverse direction, okay, or shift toward reactants. It's all saying the same thing. Okay. Final possible situation. All right, let's say my product B is 16 molar and my reactant A is 8 molar. 16 divided by 8. This time Q is equal to K, which means we don't have to shift at all. We are already at equilibrium. Now I chose these numbers on purpose. because this addresses something we talked about last class, but I just want to make sure that this concept is really solid in your mind. Okay? The definition of equilibrium means the speed of the reaction in the forward direction and the speed in the reverse are equal. The rate, this way and this way, are equal. It does not mean that my concentrations, my partial pressures, my amounts of reactant and products are equal. That is not what equilibrium means. All right? I have a greater amount, a greater concentration of B than I do of A, but this is at equilibrium. Okay, so that's a big misconception that a lot of people have. They think equilibrium means equal amount of reactant and product, and that is not what it means. Okay? So, if you need to memorize this, fine. I would prefer that you just can work through it in your mind, can rationalize it. Let's look at a problem. So for the reaction, blah, 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 it's already balanced for you. How nice. They give you a value for the equilibrium constant, and then it says, in an experiment, a certain amount of NaCl, a certain amount of NO, a certain amount of Cl2 are mixed in a 2-liter flask. Are these conditions at equilibrium, yes or no? What do you think? Is the word equilibrium anywhere in this sentence? No. These are my initial conditions. These are the amounts right at the beginning of the reaction. Okay. Which direction will the reaction proceed to reach equilibrium? What do you need to calculate in order to answer that question? Well, okay, yeah, molarities first, but then what? Q. All right, go to it. Okay, so that's not the end of the problem. They still ask which direction will this reaction shift in order to get to equilibrium. We found Q. How does this compare to the K that they gave us in the problem, which I think was something times 10 to the negative fifth? How does this compare? Is Q is what? Less than or greater than K? Less than. Okay, now don't tell me yet, is it going to it's going to shift to the right or the left. Does this situation mean I have made too much product or not enough? What do you think? Not enough. So if we haven't made enough, which way should this move? To the right. You got it. Okay? Okay. Let's move on to the main event for today. Okay, for those of you that have the PowerPoint slides in front of you, what is on this slide and the next is a series of steps, which I'm not really going to talk through them. I would rather jump to a sample problem right away and kind of work through the steps with something in front of us. Okay? But these are the steps to solving these types of problems. So I'm just going to skip through this. La 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 la. Okay. Now, you'll see at the heading of this slide, it says type 1. There are basically two types of these equilibrium problems. But I don't want you to memorize, like, is this type 1, is this type 2? Okay, I don't want you to get too hung up on that, because I'm going to show you a method that you won't have to memorize that. You will very clearly be able to see what do you have, what are you missing. Okay? And this method that I'm going to show you, I hate to use the word required. I don't want to say that the College Board requires this method, but they basically do, okay? And I hate that, because I hate saying, like, there's one way to do this problem, and that is the only way. But it's the only way they will accept. It is a good method, but still, I don't like someone telling me what to do. Anyway, so let's look at this. We've got a balanced equation, and then it says, in a certain experiment, 2 moles of sulfur dioxide, 1.5 moles of oxygen, 3 moles of sulfur trioxide are placed in a 1-liter flask. Stop there for a second. Everything given in this first sentence here, what are these conditions? Are these conditions already at equilibrium? What do you think? These are initial conditions. These are the conditions of what has been mixed together right at the beginning. Then it says, at equilibrium, 3.5 moles of SO3 were found to be present. Calculate the equilibrium concentrations of these other 2 pieces. And they also want us to give a number for K. Okay. Before we get started, because this method is basically the accepted method by the College Board, I'm going to demo this problem for you. Whatever I write, you write. Got it? Okay, good. So let's get started here. The very first thing I'm going to do is just copy over this equation that they gave us. Okay? And right next to that, I'm going to write 3 letters. Right? These are called ice table problems. If you talk to any other AP Chem teacher and you say we're doing ice table problems, they will know exactly what you're talking about. This is an acronym. These letters stand for something. Anybody want to guess what I stands for? We've said this word a couple of times today. Initial, okay? Initial conditions. Based on the title of this chapter, what do you think this is? Equilibrium, okay? Initial equilibrium. Think of this as like beginning, end. What do you think that stands for? Change. How does it change? Okay, so initial conditions. Well, initial what? In this particular problem, it's going to be initial molarities. So let's come back. SO2, where is it? Here it is. 2 moles in a 1-liter flask. I made the numbers really easy. What's the molarity? 2 molar. Okay, fine. Oxygen. What is it? 1.5 molar. And SO3, what was the number? 3 molar, okay. All right. So I've got my initial conditions. The next thing I need to think about is how are these values going to change? And in order to figure that out, we have to figure out, is this reaction to get to equilibrium, is it going to shift this way or this way? Because that is going to affect what I write on this line. Let's look back at the original slide. True or false? We have enough information right here in this first sentence to calculate Q. True or false? True. Well, what do you do with Q to figure out which way it's going to move? What do you do? Compare it to K. Do we have a K value? No, we don't. So I can't do that. But there must be some way to figure this out. Look at this sentence right here. At equilibrium. Think of it as saying, like, at the end. 3.5 moles of SO3 were found to be present. Come back here. At equilibrium, my product will have a molarity of 3.5. Isn't that greater than 3? So I got more product. Which way is this shifting? To the right or to the left? To the right. If my product amount or concentration is increasing from the beginning to the end, that means I must be making more. I must be shifting to the right. Let's think about how that's going to affect this change. If I am shifting to the right, what's going to happen to this number? Will it decrease or increase? It should decrease. So I'm going to put a little minus sign there, because that one is going to be decreasing. How about oxygen? Decreasing or increasing? Decreasing. My reactant should be doing the same thing, and my product, we know, will be increasing. Now, decreasing, decreasing, increasing by how much? I don't know yet. So I'm going to call it X, but watch what I write here. This space right here, I'm not going to say minus X, I'm going to say minus 2X. Does anybody want to guess where that 2 comes from? It does not come from right there. It comes from the coefficient. So what should I write here? 1x, or let's just say x. How about there? 2x. Okay, so the gist is, the way to think about that is, this reactant is disappearing, decreasing twice as fast as this one is decreasing. Okay, I'm going to draw a line, and I'm just going to bring everything in each column down. 2 minus 2x, 1.5 minus x, 3 plus 2x. Well, think back to what we're supposed to ultimately find here. We are supposed to solve for the equilibrium molarity, concentration of this and this. Well, I don't know what x is. There must be a way to figure it out. Come back to what was given to us in the original problem. Didn't they tell us that this guy at the end would have a molarity of 3.5? They told us that. Can you find x now? Don't pick up your calculator. You can do that in your head. What does x equal? Thank you. 0.25. What should I do with this now? Yeah, substitute it in. Plug it in. Right there. And right there. That's part of the answer. They also ask us to solve for a value for K. Before you do any solving of any kind, I'm going to ask you to do something that you will be asked on pretty much all equilibrium problems. Tell me what the equilibrium expression is. Expression meaning like this setup. Expression means no numbers yet. From our balanced equation, what would be in the numerator? I'm not looking for a number.
Polarity of SO3
SO3, thank you, squared over, yep, very good. Okay. I need these molarities to find K. Now, be careful. Which molarities should I plug in here? These or these? Yeah, your equilibrium molarities. If, and just stop for a second, if you took this number, and plugged them in, what would this be? It wouldn't be K.
Equilibrium quotient.
Yeah, well, reaction quotient. Yeah, it would be Q. All right? But that's not what we want, so we're going to plug in the numbers that we do want. The nice thing is, K does not have any units. You don't have to worry about units. So, guys, to wrap this up, let's say this question was worth 8 points in a free response section. Let's just say that. Maybe this is worth 1 point, 1 point, 1 point. The remaining 5 points are for showing this work, okay? And I've been teaching this class for a long time, and I know that as we go on with this, you're going to get faster and faster at these problems, and at some point you're going to say, I don't need to write out an ice table. Yes, you do, okay? Just do it, because these problems are going to get sometimes more complex, like, let me just, a little foreshadowing, what if I give you all of this information and your one unknown is all the way at the beginning? Meaning you basically have to work backwards. That is a much easier thing to do if you can set things up like this. Okay. You try this one. It is the same reaction as what we just did, that sulfur dioxide reaction. Different numbers, slightly different. There's a little bit of a twist to this one. Try it. Some of you have sort of noticed something. Does something seem missing in this problem? Okay, how'd you do? Okay, so not too difficult, right? Okay. The only reason I knew that with absolute certainty that this would be shifting to the left, think about it. If this were to shift to the right, this would be 0 minus x. Molarities can't go below 0. It doesn't exist. Okay? So actually, in the previous problem and this one, you could absolutely be certain about which direction it's going. Okay. Let us continue on. Okay. This is type 2. But again, I don't want you to think, okay, which type is this? Is this type 1, type 2? If you set up your ice table, you will be able to see where the holes are. What do you have? What are you missing? All right, I'm gonna demo this one for you, and then you'll do one on your own. This time I'm not given a balanced equation, but I'm given everything I need to come up with it. Okay, so carbon monoxide reacts with steam. produce carbon dioxide and hydrogen gas. Let's start there. Okay, carbon monoxide. Its formula. CO. Steam. Very good, okay. Okay, yields carbon dioxide, and how do you write hydrogen by itself? H2, very good. Balanced? Yep. Okay. Let's write out our letters. Okay. And let's go back to the original problem. Alright, it says at 700 K, the equilibrium constant is 5.1. Now that's different from the previous two problems. I'm given the value for K. I don't have to calculate it. Alright, calculate the equilibrium concentrations of all species if 1 mole of each component is mixed in a 1 liter flask. What am I dealing with here? What are these conditions? Initial conditions, equilibrium, what? These are my initial conditions. And I kept the numbers really simple. 1 mole of all of the pieces in a 1 liter flask. Okay, so everything is 1 mole. Okay. Here's a situation where I don't have to make an assumption of is it going to shift to the right or the left. Okay. I kept the numbers really easy. What is Q equal to? 1. Well, the K value was 5.1. Q is less than K. So what does that mean? Shift to the right. Yeah, we need to make more product. I'm going to shift to the right. Okay. So you guys tell me, what do I write in that spot right there? Minus X under H2O? Minus X plus X plus X. Just going to bring everything down. Okay. Let's go back to the original problem. The two previous problems we did, you were given one of the equilibrium values for either a reactant or a product. We're not given that in this situation. We are, however, given the value for K. All right. Tell me, please, because as I said, you're going to be asked to do this next step on pretty much every equilibrium problem. Please tell me, what is my equilibrium expression going to look like? All right, CO2 times H2 over CO. Very good. Okay. Well, I don't have numbers to plug in here. Okay, I actually don't need them because I already know the value for K. But let me plug in these expressions here. Okay. Coming back to what we're supposed to be solving for, we are supposed to find the equilibrium molarities of every piece here, which means I have to find x. I have to find it here. Okay? Now, this might look kind of nasty to you, like a really yuck algebra situation. Truth be told, this one is actually not too difficult, but let me just show you, make sure you understand how ugly this could get. Alright, this one is relatively simple because all of our coefficients were 1, and all of our starting initial conditions were also 1, but imagine this. What if this was 5 plus 2x squared times 6 plus 3x to the third divided by 3.5 minus 4x to the fourth power, and so on. This could get really ugly, and you've got to find a way to solve for x. The way I like to do it, guys, is by graphing it. Okay? So, if your calculators aren't out already, they should be, but if they're not, take them out. Here's what you're going to do. If you go to y equals, alright, in y1, we're going to put that number, just 5.10. In y2, you're going to put this whole thing. Now don't start typing yet. Alright? These calculators claim to operate under order of operations. It's a big lie. Okay? So we're going to appease the calculator gods. Here's what I want you to do. Before you start typing anything, I want you to recognize that it just makes your calculator happy if you put a big set of parentheses around your entire numerator and around your entire denominator. Get that typed in, and we'll continue. Okay. Here's the fastest, quickest way to find x. Are you ready? Instead of hitting graph, go to zoom and choose number 6, zoom standard. Hopefully you have not already gotten an error. Okay, now, in this particular problem, you can see the intersection points. You may not always be able to see them, and that's okay. You don't need to be able to see them. Alright, but that's what we're looking for, is the intersection points. Okay, so here's how we're going to do it. Alright, please don't jump ahead. Some of these steps are going to seem really unnecessary and silly, but just trust me on this. I've been teaching this class for 11 years. Second, calc. Alright, we want the intersection, right? We're going to choose number 5. Don't move the cursor. Don't even move it by 1 pixel. Alright, it says first curve, question mark, hit, enter, enter, enter. If you did it all right, this is what your x should come out to be. If you got that, you should be feeling pretty good about yourself. If you didn't, I will come and offer some assistance in a moment. Now, let me say something, because I bet some of you are thinking this. If you're looking at this graph, can you all see that there's more than one intersection point? Okay. And you might be saying, well, how do we know which is the correct one? Well, if you got that other intersection point, it wouldn't make sense. I mean, I don't know what it is, but let's say it's like 3.1 or what is it? 2.5 something. Try plugging in 2.5 something in right there. What's the problem? You get a negative molarity. That doesn't work. Now, I have no idea why this is, and people that are smarter than me probably know the answer, but if you don't move the cursor, when it asks you, first curve, and you just hit enter, 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 somehow the x value that comes up is always the one that you want. Please don't ask me why. If you move the cursor, sometimes you get the wrong one. I mean, I don't know how it knows, praise be to this calculator. I don't know. What are you going to do here? You've got x. What are you going to do? You're going to plug it in. Okay. So I'm going to have you try one on your own. I'm actually going to jump ahead. So this is one. I'm actually going to jump to another one. I have lots of practice in this presentation. I want you to focus on this one. I'm going to just set it up for you a little bit. So we have a reaction. Okay, it's already balanced. One of my favorite compounds. Hi. Hi, friend. Just so we're a little bit of review, what is the proper name of this compound? Thank you. Hydroiodic acid. Okay. This problem is the exact same situation with one little twist. That's a Kp value. What does P stand for again? Pressure. Okay. Ladies and gentlemen, you can set up an ice table with partial pressures. It doesn't have to be molarities. The only difference is you would be using a Kp value instead of a Kc value. The rest is exactly the same. Try this one. Now guys, remember, you don't have to make this assumption of is it going to shift in the forward or the reverse. You have all the initial conditions, and you have Kp. What could you calculate to figure out for sure which direction it's going? Q. Calculate Q and compare it to Kp. Did anybody do that? And, okay, so what do you get? When you find Q here, how does it compare to Kp? Q is greater. What does that mean? It's going to shift to the left. We've made too much product. We need to get rid of some. Okay. So ladies and gentlemen, if you did your graphing right, that's what X should come out to be, or something pretty close, maybe 0.036. Alright? If you got something completely different, or some kind of error, I will be happy to look at it for you. Alright? So, guys, that is where we are going to stop.